This is a so a metric space is a real valued function. A metric space is a real valued function. A metric space is a real valued function. Real valued function. A metric space is a real valued function. Real valued function. Defined x to x, x cross x. Defined f x cross x tends to 1. So denoted by dx comma y. Denoted by x comma y. Denoted by x comma d of x comma y. Denoted by d of x comma y. If satisfies following axioms. If satisfies following axioms. Satisfies following axioms. 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 What is the first axiom? Axioms are nothing but rules, properties, or postulates. So d of x comma y greater than or equal to 0. Greater than or equal to 0. Greater than or equal to 0. So d of x comma y. D of x comma y equal to 0. If and only this symbol is known as if and only if x equal to y. What is the second property? D of x comma y. D of x comma y. D of x comma y equal to d of y comma x. This is nothing but it is a symmetric property. Satisfies symmetric property. Satisfies. Third one. So d of x comma y. D of x comma y. D of x comma y less than or equal to d of x comma y less than or equal to d of x z. D of x z. D of x comma x z plus d of z plus d of z comma d of z comma. For all x, y, z belongs to capital X. X, Y, Z belongs to capital X. So using these concepts, we'll prove one theorem. Next we'll prove. So we'll prove a theorem. That is 1.3.1. 1.3.1 statement. Let V be a normal linear space. Let V be a that N be a normal linear space. normal n normal linear space. NLS means normal linear space. So and let B be a function and let D be a function. D be a function from n cross n cross n. So 2, 1 or I defined d of x comma y, d of x comma y equal to norm of x minus y, norm of x minus y. Then d is metric. Then d is metric. So we'll use these concepts and we'll prove. We'll proof. How to prove? Verify the all axioms of metric space. First, what we should do? RTP, or we need to prove. We need to verify all the axioms of metric space. All the axioms of metric space. What is the first one? Verify. So d of x comma y. What is this? First one is now metric space property is d of x comma y equal to if and only if norm of x minus y equal to 0. X minus y equal to 0. If and only if x minus y equal to 0 by axiom 1. If and only if x equal to y by property 1 or by definition. Property 1. Definition. Next. So second property. D of x comma y. D of means x comma y. That equal to norm of x minus y. Norm of x minus y. That equal to norm of, if you take minus 1 common in these two, minus 1. What we need to write? Y minus x. You can write minus y minus x. Y minus x. So that equal to, we need to write minus 1 is within modulus of norm of y minus x. So modulus of minus 1 is 1. So 1 into that equal to y minus x. Equal to y minus x. So by axiom 2. That means what we prove here? D of x comma y is nothing but d of y comma x. This property is second one. That is already we wrote symmetric. Dx comma y equal to dy comma x is symmetric. With used normal properties we come. Next. Next third part by axiom 3. So norm of x minus 1. Norm of x minus 1. Norm of x minus 1 is less than or equal to. Norm of x minus y is less than or equal to norm of x minus z. Norm of x minus z. Plus norm of z minus y. Minus norm of, so x minus 1 we go norm of z minus y. z minus 1. For all x, y, z belongs to, for all x, comma, y, comma, z belongs to z. So hence, so from this it follows that from this it follows that from this follows that 3x comma y follows that d of x comma y of x comma y less than or equal to d of x comma z plus d of z comma y for all x comma y comma z belongs to n. X comma y for L belongs to n. So thus D is a metric on n induced by the norm. Thus metric is a D is a metric induced by the norm, induced by the norm, induced by the norm. Okay, next. Next, LP spaces definition. What is LP spaces? LP spaces definition. So 1.4. LP spaces definition. LP spaces. We now introduce the classical Banach spaces LP. What is this? This is nothing but classical Banach spaces LP. So LP equal to, this is known as classical Banach spaces. LP equal to LP of in closed interval 0, 1. 0, 1. P is greater than or equal to 1. P is greater than or equal to 1. So let us introduce the LP. Let us introduce the LP. Introduce the LP. Let us introduce the LP. As follows. A real valued measurable function f. A real valued measurable M-E-A-S-U-R-A-B-L measurable function. Measurable function f on 0, 1. F on 0, 1 and 0, 1 is said to be LP. Is said to be LP. If 0 to 1 integration 0 to 1 modulus of modulus f whole power p less than infinity. What is LP space? A real valued measurable function f on 0, 1 is said to be LP. A real valued measurable function f on 0, comma 1 is said to be LP if 0 to 1 mod of f whole power p less than infinity. Less than infinity. So it is easy to say. So LP is a linear space with two operations, addition and multiplications. LP is a linear space. LP is a linear space with two operations. LP is a linear space. LP is a linear space. It is a linear space with the two operations. With the two operations. The two operations. Addition and scalar multiplications. Operations, addition, and scalar multiplications. Scalar multiplications. Addition and scalar multiplications. First one, f comma g means let functions who are f comma f of f is function, another f belongs to LP. What is LP? A real valued measurable function f on 0, comma 1. What is this? A real valued measurable function f on 0, comma 1 is said to be LP. If 0 to 1 mod f whole power p less than infinity. Now here belongs here. Then integration mod f plus g if is said to be LP if 0 to 1 mod f less than infinity. A real valued measurable function f on 0, comma 1 is said to be LP if 0 to 1 mod f less than infinity. LP is a linear space with the two operations and addition and scalar multiplications. So whole power p, whole power, what is p? P is less than or equal to 1, less than 2 to the power of p plus integration mod g whole power p mod whole power p is less than or equal to plus infinity. Less than or equal to plus infinity. Since we have modulus of f plus g whole power p is less than or equal to 2 to the power of p modulus mod f power p plus g power p mod g power p mod g power p. Next, second property. What is second? Second one is if f belongs to LP. If f belongs to LP. F belongs to LP. And A belongs to I. And small a belongs to I. Small a belongs to I. Then integration mod A f or p integration now f whole power p less than infinity. So here f and g belongs to here Thus f comma g belongs to LP. LP. All right. Now, that is perfect. So to make LP as normal linear space, to make LP, what is LP? A real measurable, valued measurable function. A real valued measurable function f on 0, 1 is said to be LP if 0 to 1 mod of f less than infinity. So we make LP normal linear space. NLS means normal linear space. Define a norm. Define a norm of f. Norm of f belongs to LP. As follows. So norm of f p that equal to modulus of f p whole power 1 by p whole power 1 by p. Next, so most important 1.4.2 Holder's inequality. Holder's inequality theorem. Holder's inequality. Holder's inequality theorem. Holder's inequality theorem. The statement assuming p is greater than 0, assuming p is greater than 1 and 1 by p plus 1 by q equal to 1. If f belongs to LP, f belongs to LP. LP means a real valued measurable function is said to be LP. It's called LP if 0 to 1 mod whole power p is less than infinity. Less than or equal to plus infinity. Less than or equal to plus infinity. Less than infinity. 0 to 1 mod f whole power p less than infinity. So LP. If f belongs to LP, then FG belongs to L1. And now FG L less than or equal to norm P, norm Q, less than or equal to norm F P. norm G. Q. So proof. Shall we discuss proof? We discuss proof. What is the proof? Let alpha equal to norm of P. Let alpha equal to norm P. Norm F suffix P. Beta equal to norm G suffix norm G suffix Q. Suffix Q. If alpha equal to 0, or beta equal to 0, then F equal to 0, comma, G equal to 0. Almost everywhere. Hence it is follows. Almost everywhere. Almost everywhere. Almost everywhere. Almost everywhere. Hence it follows that. Hence it follows that. Hence it follows that. Follows that. Hence it is follows that. Fg equal to 0. Fg equal to 0. Almost everywhere on 0. Close interval 0, comma 1. And the conclusion of theorem is trivial. Assume that alpha is greater than 0, beta is greater than 0. Let alpha is greater than 0, beta is greater than 0. Beta is greater than 0. Greater than 0. For x belongs to 1. X belongs to 0, comma 1. Right. Next. So proposition 1.4. So alpha equal to, from proposition 1.4.1, we're taking alpha equal to mod f of x whole divided by alpha, comma, not alpha, this is small a equal to, then small b equal to modulus of g of x whole divided by beta. Whole divided by beta. So we obtain so norm of mod f of x g of x whole divided by alpha into beta, because we are multiplying nothing but AB. Alpha into beta is less than or equal to mod f of x whole power p, f of x whole power p whole divided by p alpha power p plus g of x mod whole power q whole divided by q into beta power q. So then beta power q, no, alpha into beta power. So then integration, we are applying both sides integration parts. integration 0 to 1, integration 0 to 1, mod f of x into g of x whole divided by alpha into beta dx is less than or equal to 0 to 1, 0 to 1, mod of f of x whole power p, p alpha power p into dx plus integration 0 to 1 mod g of x whole divided by q into beta power q, this whole power q dx, which is less than infinity. Less than infinity. So now consider integration whole power less than infinity. Then integration mod g whole power q is less than infinity. From this we get integration fg less than infinity. Hence fg belongs to L1. Further, we choose further. Yeah, further. So further. So norm of fg whole divided by alpha beta, that equal to integration 0 to 1 f of x into g of x into g of x whole divided by alpha beta less than or equal to 1 minus alpha power p whole divided by p into alpha power p plus 1 divided by q into beta power q, that equal to beta q, that equal to 1 by p plus 1 by q, that equal to 1. So hence that implies norm of fg less than or equal to norm of f p norm of g q for f belongs to LP. So come on, G belongs to LQ. Okay, today what we discussed? What we discussed? A normal linear space. In the normal linear space concepts. What is properties of normal linear and properties of metric space based upon one theorem we proved. Next, based upon one theorem also proved. Next, what we did, the Holder's inequality, most important, Holder's inequality theorem is also proved. Next, what we have important is for Minkowski inequality. Minkowski homework, most important theorems. important theorems. For exam point of view, in this chapter, in the exam point of view, in this chapter, 1.4.3. 1.4.3. What is this? Minkowski inequality. Minkowski inequality. We didn't have a time to show the inequality. Minkowski inequality. And almost 1.4.4. Consider homework. This is 1.4.4 theorem. 1.4.0. LP spaces are complete. LP spaces are complete. Okay, LP spaces are complete. Next. Spaces. Next. 1.5.3. 1.5.3. 1.5.3 is Ray's representation theorem. Ray's R-I-E-S-Z. R-I-E-S-Z. Ray's representation theorem. Ray's representation theorem. Ray's representation theorem. This one, Ray's representation theorem. So, are you audible? Anybody there? So, homework, what we discussed today in normal linear space, important concepts of normal linear space and unitary space. Based upon those concepts, definitions, we proved one theorem and one more theorem also, Holder's inequality we proved. Next most important theorem, 1.4.3, Minkowski inequality theorem, and 1.4.4, LP spaces are complete. Next 1.5.3, Ray's representation theorem. So, this chapter is over. You have to read this one, right? Thank you. Anybody is there? Any doubt? Sudhakar. Thank you. Thank you.